So how do we solve differential equations? Well, there's lots of different types of differential equations, and they take some special methods and techniques. Now we're going to look at one type of differential equation, and that is what we call separable differential equations. So a separable one is one that we can move the x's and the dx's onto one side, and we can move the y's and the dy's onto another side. We call a first-order separable differential equation, there's a mouthful, is one of this form, dy dx equals some function of x times some function of y. In this equation, we can see that the right side is a product. Notice it's not a sum. It's actually more difficult. If there was a plus sign in between here, we couldn't do much about it right now. So it's got to be a product. So when we're separating variables, we're gonna factor it with the x's and y's, separate those, and then we'll treat the dy dx as infinitesimal variables, meaning like they're actual numbers, all right, which they kind of are as the limit goes to infinity. This is delta y at infinity or infinitely small. All right, well, what does that mean? Well, let's take an equation here like this one. We've got dy dx equals x squared over y squared. And we want to solve this by separating variables, and then we're going to get a particular solution for these a, b, and c values here. So if we take dy dx, and which is x squared over y squared in this case, and we got one fraction equal to another fraction. Let's try to cross multiply. So if we cross multiply here, we get y squared times dy, and we get x squared times dx. All right, and now we want to get rid of that dy and that dx. So the opposite of a derivative is an integral, so we're going to integrate to kind of undo that dy and that dx. Now notice this looks very familiar. We've been doing these integrals here. This is the antiderivative of x squared with respect to x, or dx. Okay, and so that's x cubed over 3. And the antiderivative of y squared dy is going to be y cubed over 3. Now we also need to have this plus c. Well, we're going to go ahead and put it over here. It doesn't really matter. Now, if we put a plus c on both sides, like a c1 and a c2, then we would just subtract this over, and we'd have a new constant. All right? So we can kind of combine those constants, and we're just going to put one constant usually over on the x side, and you'll see why. So we can clean this up a little bit more. Now we will call this constant 1, because we're going to want to solve for y here. So we're going to multiply this by 3. We get a different color here. We'll go times 3 times 3, and that gives us y cubed equals x cubed. Now we have 3 times that and 3 times c. We've got to distribute here. Well, 3 times c is just another constant. We could call it 3c1, but we're just going to call it c2 as another constant, okay? So we'll use the 1 and 2 because these are different numbers, but they're just constants, okay? And, okay, that's a useful equation. That's in pretty nice form. But let's go ahead and cube root both sides, and we can write this as y equals the cube root of x cubed plus c2. So there is the general solution. So the general solution is a family of functions. Okay, so this is a family of functions here, and so this is our constant here gives us a general solution, and so now we want to find a particular solution. So a particular solution means we need to take into account the initial conditions. So we know that we're looking for a graph or an equation in this family that goes through the point 0, 2. So that means we got to find the c value that will go through 0, 2. Now we can use either of these here. You might find it more convenient to use a form that was a few steps up. Again, we got this C2, so we need to use one that has C2. I don't want to use this one yet. Okay, so using this C2, let's use this form. It's a little bit easier. So we're plugging in the points 0 for x and 2 for y. So we have 2 equals the cube root of, no, I'm sorry, let's not use the cube root 1. Let's use the 2 cubed equals x cubed plus c2. And that's 8 equals c2. So this gives us a particular solution. Now I'm going to go put that c2 in the y equals version. X cubed plus 8. There you have it. Okay. Now, that is the graph that's in this general form that goes through 0, 2. What if it goes through 0, negative 2? Well, then we can plug that in. We've got negative 2 cubed plus 0, equals 0 cubed plus c2. That's negative 8 equals c2. This is a different function. Now let's go ahead and put that in our final equation. Y equals the cube root of x cubed plus 8. Nope, minus 8. Plus 8 was the last one. Okay. That's the idea there. All right. And let's try one more here. So we have 0, 0. Let's plug that in. We know 0 cubed equals 0 cubed plus c2, which tells us c2 is 0. And now our equation is y equals the cube root of x cubed plus 0. Well, that's just the cube root of x cubed, which is x. Y equals x. So we can simplify that all the way. So y equals x actually belongs to this family because it's the equation when c2 is 0. So these are particular solutions here. Okay. And they are specific equations that will go through these given values. All right. Let's try one more. So the last example had a quotient. Here's one that has a product. So let's find the general and particular solution of dy dx equals x squared times y. All right, well, in this case, let's find our general solution here. I'll come over here, dy dx equals x squared times y. Well, we need to get the x's on one side and the y's on the other side. So let's maybe multiply by dx on both sides. So if we multiply by dx here and dx here, we'll end up with dy equals x squared y dx. And if we divide both sides by y, then we have dy over y, or you might find it useful to write this as 1 over y dy. It's the same thing, equals x squared dx. And now we can integrate. Okay. And if we integrate, well, what's the integral of 1 over y? The integral of 1 over y is the natural log of y, absolute value of y there. Integral of x squared is x cubed over 3, and we need a plus c. So how do we solve this for y? Well, this is, you can think of this a couple ways. We can use the definition. This is the log base e of y. So we can use the definition and swing this over, and this is y equals e to the x cubed over 3 plus c. And so there's our answer for y. Or we can take this, we can think of it this way. Instead of using that definition there, we can exponentiate. And what exponentiate means is let's take this equation here written in black and let's raise those to the power of e, and that will be a true equation. And the e to the natural log of y, those are opposites, so they cancel each other out. Okay, we're left with y. Now, by the way, here we had absolute values of y. Notice I didn't put absolute value here. That's because e to any power is always positive. This is a positive answer. There's nothing that, no x or c value that will make it negative. So there's our general solution. All right. So let's find a particular solution here. When x is 0, y is 1, so we can have y equals, y is 1, and that equals e to the 0 over 3 plus c. Okay, well, this is y equals e to the 0 plus c, which is just c. And if we take the log of both sides here, take the log, so we have the natural log of 1 equals, and the natural log of e to the c is c. And what is the natural log of 1? The natural log of 1 is 0. So this tells us that c is 0. Okay. Give ourselves a little room here. Okay. And so if c is 0, then our equation becomes y equals e to the x cubed divided by 3. So there's our particular solution. That's plus c is 0. Okay. What if we have, this is the point 0, negative 6. So that gives us, we have, again, here's our general solution. We're going to put in negative 6 for y. We'll put 0 in for x. Okay. And so we get negative 6 equals e to the 0 over 3 plus c. So in other words, e to the c is negative 6. And we're going to take the log of both sides, the natural log of that, the natural log of that. And so the natural log of negative 6, Can we take the natural log of negative 6? No. Okay, the natural log of negative 6 is undefined. Okay, so this has no solution. Or you could say does not exist. Okay. All right. So there is no graph of, no solution graph that will go through 0, negative 6. All right, so that's the idea there. So we'll leave it at that there. We'll look at some examples later there. But now we can solve these equations that are separable. Again, you have to be able to multiply and divide, not adding or subtracting. We've got to multiply or divide to get these over to either side so we can integrate like we did here. Okay.